AI is evolving right now. It's like a Pokemon evolving to the next stage, or Goku turning Super Saiyan. It's really exciting, so you don't want to miss out on what's going on right now. In this video, I'm going to go over a few recent breakthroughs in AI. If true, this is going to be huge. This is going to make AI way smarter than even the smartest models we have today. Now, these are quite technical papers, but as always, I'm going to break this down and explain it in simple terms so that you can understand it even if you don't have any technical background. So let's jump right in. Now, the first paper you should pay attention to is this one by Google Research called TITANS. Not those Titans. Anyways, this is a pretty crazy breakthrough because it gives AI a human-like memory. Plus, this AI can keep learning new things even after training. And spoiler alert, this beats everything out there. So, for example, if you look at this table, here are various benchmark scores, and the values highlighted in color indicate the best performer. So you can see that across the board, these Titan models beat all the existing AI architectures we have out there, like the Transformer model or Mamba, which you might have heard of before. Here's another chart showing the performance of these Titans models in this dark red line at the top. The higher the value, the more performant it is. So across both these charts, you can see that it beats leading models like GPT-4 or 4o mini or Llama 3. So this is an insane improvement and definitely huge if true. Now, before we talk about this new Titans architecture, here's a brief background on where we are at in the world of AI today. So in 2017, Google Research released this paper, Attention is All You Need. This is the most iconic and influential research paper in the world of AI as we know today. It has led to the AI explosion that we've witnessed in the past few years. This paper basically introduces the Transformer architecture, which is used in all of the top AI models out there, including GPT-4o or o1, or Google's Gemini, or Claude, or DeepSeek, or Llama. You name it. Pretty much all the large language models out there are derived from this Transformer architecture. And this is quite revolutionary because the Transformer is excellent at understanding context by focusing on relationships between different parts of the data. This makes it perfect for understanding language and helping with things like writing, coding, and reasoning. But that being said, there are also some huge limitations with this Transformer model. Yes, it's really good at digesting and outputting information you feed it, but if you feed it a lot of data, it gets super inefficient and incredibly slow. These Transformer or attention models are quite accurate, but they are also expensive if you have a lot of data. So here it says, accordingly, by design, the output of a transformer is exclusively conditioned on the direct dependencies of tokens in the current context window. This accurate modeling of dependencies, however, comes with quadratic time and memory complexity in terms of context length. In other words, transformers are limited by a context window. There's a limit on how long your prompt can be. If your prompt is too long, then it just can't handle it. It's going to be too computationally expensive and inefficient. For example, when you're using ChatGPT and you enter a super long prompt like this, you're probably going to see this error message. The message you submitted was too long, please submit something shorter. That's because there's a limit on how long your prompt can be. This is known as the context window. So for your reference, GPT-4o, I believe, has a context window of 128,000 tokens. Claude has a context window of 200,000 tokens. And then most recent Google Gemini 2 has a context window of 2 million tokens, which is already huge. So for example, this can fit like 2 hours of video. It can fit over 60,000 lines of code and over 1.4 million words. That being said, it's still not enough for some real-world tasks. For example, if you want to plug an entire novel or hundreds of pages of historical documents or the entire codebase of an organization, then like I mentioned, current transformer models cannot process so much data at once. So this new Titans architecture aims to overcome this limitation. Here it says Titans can effectively scale to larger than 2 million context window size with higher accuracy. Plus, most AI models that you use today lack long-term memory. So for example, when I use Perplexity, after a long chat, if I ask it, what did I say 10 prompts ago? It's going to answer, I'm unable to recall previous interactions as I don't have memory of past conversations. So wouldn't it be nice if there was a mechanism for AI models to actually remember things long-term? Well, that's exactly what this TITANS paper aims to solve. It aims to give AI models the ability to remember things long-term, just like humans. In fact, they based this design off of the human brain, how humans remember and learn things. Specifically, this paper aims to address these main questions. What constitutes a good structure for memory? What is a proper memory update mechanism? What is a good memory retrieval process? How to design an efficient architecture that incorporates different interconnected memory modules, which we'll go over in a second. Is a deep memory module needed to effectively store and remember long past? All this means is they're trying to understand what's the best way to give an AI model memory. What's the best architecture or design to use so that an AI can remember things and update its memory. And also, what's the best way to retrieve relevant memories when you ask it questions about something. So next, they go over their rationale and how they designed this. So in this section, it's called learning to memorize at test time. And this word test time is super important. That means the AI can continue to learn and remember and update its memory even after training. It can update as you're using it. Now, if you're not familiar with this term test time, here's a really quick explainer. I want to make sure you get these fundamental AI terms in order to really understand the paper. In the simplest sense, an AI model basically consists of a neural network like this. This is a network of dials and knobs, also called model weights, which determine how much information flows through to the next layer of neurons and then to the next layer and so on. And by the way, this neural network is based on how the brain works. Our brain is also a network of neurons that determine how much information flows through to the next set of nerve cells. Now, this diagram I'm showing you right now is really simple. It only has a few neurons and a few layers. But in reality, these large language models like GPT-4o or DeepSeek have a lot more neurons and layers. So you might be wondering, how do you determine the values of these dials and knobs? In other words, how does it know how much information or what information should flow through to the next layer? Well, that's exactly what the training phase is for. During training, this neural network is fed a ton of data, and for each round of training, its output is compared with a verified answer. So sometimes it gets the answer right, sometimes it gets it wrong. And for each round of training, if it gets the answer wrong, then these dials and knobs are tweaked slightly to minimize the error. This makes sure that the AI model is as correct as possible after training. So that's the training stage, or train time. And after training, these dials and knobs do not change anymore. When you use the AI model, like when you prompt ChatGPT, your prompt basically gets broken down into tokens, which then flow through this neural network. And again, this determines how much information goes through to the end layer, which then magically spits out the answer for you. Now, this stage where we use the AI model is called test time or inference time. So to sum things up, during training, this is where these dials and knobs, or model weights, would change in order to become more correct based on its training data. This is how an AI model, quote unquote, learns new things. But during test time, or when you're using the model, these dials and knobs do not change. In other words, the AI doesn't really learn new things or improve. At least that's how most of the AI models you use today work. But back to this paper, here they've designed something that actually can change these dials and knobs, or at least the memory of the AI model, during test time. This is huge if true. That means these Titan models can continue learning new things even after training. In theory, they could get smarter and smarter. So next, let's jump into the details. There's actually a few components in this architecture to make this work. One component is this long-term memory module. Of course, this is for storing long-term memory. Now, they've included a few interesting mechanisms in place that are inspired by human learning and memory. So one of them is this learning process and surprise metric. Now, if you think about it, we don't want to remember everything that happens in life. Otherwise, our brain is going to have a memory overload. we only want to remember important things. For example, let's say you walk to work every day and it's the same routine, the same road, the same people, everything is just the same every day. Well, in that case, there's not much to remember, right? But what if one day you were robbed on your way to work, or there was a car crash? Then your brain would clearly remember this incident. It's not the norm. It's not what you would expect from your daily routine. So here they say, an event that violates the expectations, in other words, an event that is surprising, is more memorable for humans. So inspired by this same logic, they designed this AI so that it only remembers surprising events that are not normal, events that violate the expectations. But here's the thing, going back to our example, if you are walking to work and then you get robbed or you encounter a car crash, well, the start of the event would be the most surprising, the most shocking, right? But you would also want to remember everything else that happened. You want to remember the entire event, like who was the person who robbed you? Where or how did they rob you? Or where did the car crash happen and how did it happen? How can you avoid this next time? So similarly for the AI, you don't want it to just remember the most surprising point in time. You also want it to remember important things that come after the surprise. So here they say, this surprise metric, however, can result in missing important information that comes after a big surprising moment. From the human memory perspective, an event might not consistently surprise us through a long period of time, although it is memorable. The reason is that the initial moment is surprising enough to get our attention through a long time frame, leading to memorizing the entire time frame. So following the same logic, they've also basically designed this so that the AI doesn't just remember the most surprising point in time, but it also remembers the entire event that was triggered from the surprise and incorporates this into its memory. This is very similar to how humans remember things. Now, remembering things is great, but of course there's going to be a limited capacity. You can't just keep remembering things indefinitely, otherwise your brain would be overloaded. So there also needs to be a mechanism for us to forget things that are not as important anymore, so that our brain has room to remember new information. Similarly, they've added a forgetting mechanism for this TITANS model. So here it says, when dealing with very large sequences, it is crucial to manage which past information should be forgotten. To this end, we use an adaptive forgetting mechanism that allows the memory to forget the information that is not needed anymore, resulting in better managing the memory's limited capacity. So basically, this algorithm determines, what information is not important or not used anymore for a long period of time and should be forgotten. So that basically sums up the main parts of this remembering mechanism and the forgetting mechanism. Next, here's another fundamental design of this TITANS architecture. It basically consists of 3 hyperheads, as they call it, or 3 types of memory working together. So here it says TITANS consists of 3 hyperheads. Number 1 is the core. This module consists of short-term memory and is responsible for the main flow of processing the data. We use attention with limited window size. This is focused on what's happening right now. It uses a component called attention, which helps it pay close attention to the current context. This is like a student focusing on the current paragraph that they're reading. This is like a short-term memory that can only process a limited amount of information at any given time and quickly forgets old details. In other words, it has a short attention span and it's only focused in the moment. And the core memory uses this attention tool to decide what parts of the current input are most important. What parts should it focus on? And then next we have this long-term memory, and as the name implies, this memory is responsible for storing things that it has learned over time. And it's always learning and updating its memory and also forgetting things that are unimportant using the forgetting mechanism that we just covered. So this memory kind of works in the background. It's not focused on the current moment, which is what the core branch is for, but it's ready to provide information from the past whenever it's needed. And then finally, we have persistent memory. So this memory stores general knowledge about the steps needed to solve something like a math problem, or how physics works, or how the world works. This knowledge does not depend on the specific details of your prompt. So think of this knowledge as like the rules or approaches needed to solve a task. This is a constant knowledge base that doesn't really change much over time, which is why it's called persistent memory. Now, these three branches are the most important parts of this TITANS architecture, so I hope this gives you a good explanation of what these branches of memory actually do. Now, next, the authors produce three different variants of how these three memories can work together to remember and learn and forget things. And each variant has its own pros and cons. So here they say, how can one effectively and efficiently incorporate memory into a deep learning architecture? We aim to answer the above question by proposing three different variants of TITANS. Later in our experiments, we show that each of these variants has its own advantages and disadvantages, and also can show a trade-off between the efficiency and effectiveness in very long contexts. So here are the three different variants. One is called memory as a context. The second one is called gated memory, or memory as a gate. And then finally, we have memory as a layer. So let's go over each of these. The first one is memory as a context, and here's an illustration of what that would look like. So this blue section here is the core memory. Again, just a reminder, this is the memory that's focused in the moment. And then this yellow strip is the long-term memory. It's kind of working in the background, and it can provide information from the past to the core memory whenever it's needed. And this pink strip at the bottom here is the persistent memory. So again, this is like general knowledge about the world, and this knowledge doesn't really change much. So in this memory as a context architecture, all three types of memory work together. All their information is combined or concatenated into this long piece of data. So for example, we have this core memory. This is the short-term memory that's focusing on the current context and what parts are the most important, but it's also pulling in some general knowledge from the persistent memory based on whatever is relevant. Plus, it's also pulling some snippets from its long-term memory, which might be relevant. And then all of this data is added together and then passed through this attention block. And what this does is it decides what part of the information it should store or update in its long-term memory. So in a really simple sense, memory as a context is like you're working on a certain task, but you also have some notes or guidance from the long-term memory or from the persistent memory, which you can refer to help you with the task. So that's one architecture on how you can blend these three types of memory together. The second architecture is called gated memory, or memory as a gate. And here's how it works. So the core memory, or basically the short-term memory, the in-the-moment memory, it gets some help from the persistent memory. It can pull some information from its general knowledge of the world that's relevant in helping it solve this prompt. However, it doesn't pull any information from the long-term memory. This long-term memory actually works separately, and then afterwards, the information from the core memory and the long-term memory are combined by a gate that decides how much information from each memory should be used to make the final output. So think of this as like two students working on separate tasks, and then a supervisor combines their work based on each of their strengths and relevance to the project. So the supervisor is basically the gate. It determines how much information from the long-term memory and from the short-term memory should be added to the response. And this kind of makes sense, right? Because we should have a mechanism to control how much of the current information or our past memory affects the current output. And then finally, they also suggest a third variation called memory as a layer. So at the start, the core memory again refers to the persistent memory for any relevant guidance. And then this data is fed through the long-term memory. Now here's where it's different. In this case, the entire piece of data is fed through the long-term memory as an extra or separate layer that processes the input. It summarizes and compresses the past and current information. So This is like a student preparing a summary of what they have read before moving on to the next section. And then finally, all this information is again passed through this attention mechanism, which determines the output. So this is called memory as a layer because this long-term memory acts as a separate layer which processes all the information which is passed on from the core memory. So I hope that makes sense. That sums up the 3 variations. And note that they're introducing these 3 different variations because all of this is new territory. We don't really know what's the best way to incorporate memory into an AI. And there are pros and cons to each one. So for example, going back to memory as a context, this is really good at understanding context and handling long dependencies in data. So it's well suited for tasks where understanding relationships across a lot of data is important. It's also great at handling long contexts, such as needle in a haystack tests, which I will explain in a second. So some use cases for this would be like analyzing things in legal documents, or understanding scientific research papers, or tasks that basically require integrating information from multiple sources or retrieving information from a lot of data. Now, the disadvantage of this variation is that it might have slightly slower training time compared to other variants. This is due to the added complexity of adding multiple sources of information. So, for example, you can see here it's referring to the persistent memory and referring to the long-term memory during training, and all of these steps require more compute and more time. Let me tell you about this awesome tool called ChatLLM by our sponsor Abacus AI. This allows you to use the best AI models out there all in one integrated platform. This includes the latest O1 Preview, O1 Mini, as well as other state-of-the-art models like GPT-4o and Claude Sonnet 3.5. Plus, they have a new Route LLM feature, which automatically picks the best LLM to use based on your prompt. You can also generate images right from the chatbot, and they're using the best generator out there, Flux Pro. Plus, you can even generate videos with a single prompt. Plus, it has a really cool artifacts feature, so if you're coding or building something with it, it allows you to view and interact with the app side by side. They also have a new coding tool called Code LLM. This works exactly like VS Code, but it's supercharged with AI. You can chat with an AI on the side to help you generate or edit code, or you can even press tab to autocomplete code. This allows you to code way faster. They also have a new feature called AI Engineer, which allows you to create your own custom chatbot fine-tuned on your own custom data or instructions. This is a really powerful way for you to use the best AI models out there all in one platform. Try it out via the link in the description below. Next, moving on to memory as a gate, this also performs quite well in understanding context and common sense reasoning, similar to the previous variation. And because it uses this gate mechanism to control how much short-term memory to combine with long-term memory, this allows for a more flexible integration of information at different timescales. So this would be great for like chatbots or virtual girlfriends or virtual assistants. This is great for conversational AI where both the immediate context as well as your past chat history would be relevant. Similarly, this is also great for time series analysis, like analyzing stocks, where both recent trends and long-term patterns are important. However, the disadvantage of this is it's slightly worse at handling dependencies with a lot of data at once. Therefore, it's less effective in handling long context tasks compared with the previous variation, memory as context. And finally, we have memory as a layer. So this offers faster training because it doesn't have to merge the core information with the long-term memory. It just passes everything to the long-term memory to process as a separate layer. So the training time would, in theory, be faster. So this is the best alternative when compute is a limitation or if processing speed is your main concern. That being said, this tends to perform worse, especially for common sense and reasoning tasks. So that sums up the architecture and design of these Titan models, and you might be wondering, well, how good is this? So in this table, it's a pretty big table with a lot of data points, but basically the top row shows different benchmarks for language modeling and reasoning tasks. So here they compare the TITANS models with other existing AI model architectures like Transformer or Mamba. Anyways, the best scores are highlighted in color. So note that for some of these benchmarks, a lower value means it's better. Some of these, a higher value means it's better. But anyways, just focus on the values highlighted in color. So you can see that for most of these, the TITANS architecture has the best benchmark scores compared to all these different models. So the takeaway from this is that these TITANS are the most performant compared with all the existing AI models we have right now. The crazy thing is, like I mentioned previously, this can easily incorporate a context window of over 2 million tokens. So you can input a lot of data at once into your prompt, and it would still be able to handle this efficiently. So this model is especially good at needle in haystack tasks. Now, if you haven't heard of this term before, needle in haystack is basically finding a really small snippet of information that's buried or hidden in a lot of data. So it's like trying to find a needle in a big pile of hay. Finding that needle would be really hard or close to impossible. So some examples of this would be like trying to find a specific piece of information in a ton of historical documents, or trying to find a very rare mutation in a genetic sequence, which could be incredibly long. So if you look at this table, here are some benchmark scores for needle in haystack tests. And again, for the most part, you can see that these TITANS models have the best score compared with other AI architectures. Here's another figure showing the performance of TITANS compared with other leading models like GPT-4 or 4o or Llama. So the dark red line at the top is the performance of TITANS, and the higher this value is, the more performant or accurate the model is. And you can see that especially for longer context lengths, the Titan models are way better than the rest of these AI models. So this is a really impressive breakthrough. And because this model is designed to update its memory at test time, so even after training, this means that it can continually learn and adapt. This is an AI that can get smarter and smarter over time. So I think with this paper, we're past the age where we just have limited AI models with limited intelligence. I think this TITANS paper could cause another intelligence explosion where we're going to have a ton of new AI models that can keep learning. It could be as influential as this original Attention is All You Need paper, which caused the AI explosion that we've seen in the past few years. And by the way, note that both papers are by Google Research. So Google is absolutely killing it in this AI space. And just like with the Transformers paper, at the end of this TITANS paper, they mentioned that we intend to make the code we used to train and evaluate our models available soon, which is fantastic. Speaking of continual learning, this brings us to another new architecture, and this time it's by this AI lab called Sakana. Now, I featured Sakana before. They were actually known for this other project called AI Scientist. This is an AI that can conduct full scientific experiments and write complete scientific papers all by itself. Pretty incredible stuff. If you want to learn more about AI scientists, definitely check out this video. But anyways, back to here, they introduce a new approach called Transformer², self-adaptive large language models. And the aim of this paper is similar to the TITANS paper. They want to design an AI model that overcomes the limitations of current transformer models, which are static. In other words, these dials and knobs do not change after training. All the AI models we know of today, they were trained on a specific dataset, and they can't really adapt to new tasks or learn new things after training. Now, you could train an existing model further, and this is a process called fine-tuning. But this also requires significant retraining, and this could take a lot of time and compute. In other words, retraining an AI model or getting it to learn new things is not really efficient for current AI models. What if we can get an AI that can just learn and adapt in real time? By the way, that's how the human brain works. The human brain continues to change over time as we experience and learn new things. It can continuously adapt to new environments and learn new habits. By the way, this is called neuroplasticity. This is the ability for the brain to change and adapt and reorganize itself in response to new experiences or environments. So for example, once you learn music and you start to play more music, the part of your brain called the auditory cortex actually becomes larger and more developed, because this is the part which is involved in learning and processing music. Or if you learn a new language, your brain actually creates new connections between neurons to store the new language, rules, and vocabulary. Or when someone becomes blind, the brain can reorganize itself to compensate for the loss in vision. So for example, the parts of the brain that are responsible for other senses like smell or touch would become stronger and more sensitive to compensate for the loss in vision. These are all examples of the brain being able to change and reorganize itself in response to certain events. So in this paper, they aim to do the same thing. They designed this new architecture called Transformer², and here they say this is a machine learning system that dynamically adjusts its weights for various tasks. So here they continue, the name Transformer² reflects its two-step process. First, the model analyzes the incoming task to understand its requirements, and then it applies task-specific adaptations to generate optimal results. By selectively adjusting critical components of the model weights, our framework allows LLMs to dynamically adapt to new tasks in real time. We'll go over the technical details of this two-step process in a second, but first, here's the rationale behind the design. So if you look at this illustration, current AI models today, it's just a huge network of dials and knobs, and if you prompt a model like ChatGPT with something, your prompt gets broken down into tokens, and it flows through this entire network, which then spits out an output. But that's not really how our brains work. Our brain is actually made up of different parts, and each part is responsible for a certain thing. For example, we have the frontal lobe, which is responsible for motor functions and problem solving, reasoning, and planning, and then we have the parietal lobe, which is responsible for sensory information like touch and temperature. And then we have the temporal lobe, which is involved in audio processing and also memory and recognizing faces. And then we have the occipital lobe, which is responsible for visual processing, and so on and so forth. Basically, different parts of your brain handle different functions. And when you experience or process something, it doesn't trigger your entire brain to turn on, right? Only parts of the brain responsible for processing relevant information will be triggered. So back to Transformer². They've basically designed this so that the neural network can be segmented into different parts. Some parts might be better for language understanding, some parts might be better for reasoning, other parts might be better for coding and math. Now, how do you actually use this? Well, it involves two main steps. So the first step is analyzing your prompt or incoming task. So for example, in this really simple illustration, you can see that if you plug in your prompt, it will first analyze it and determine that this is a math question. Afterwards, for the second step, it's going to figure out what part of the brain to emphasize and what parts of the brain to de-emphasize by changing the model weights. And from doing that, the new AI model is now better for math problems. And then it runs your prompt through this again to answer your math question. Now, going back to step 1 for a second, which is identifying the question, like is it math or coding or language? How exactly does it do that? Well, the authors suggest 3 main methods on how to classify the incoming task. The first method is called prompt-based adaptation. Here they call it a specifically designed adaptation prompt classifies the task and selects a pre-trained Z vector. So think of this as like an extra prompt that's designed to tell the AI what task it needs to do. For example, if you input a math problem, then this prompt would tell the AI, this is a math problem. And after it has classified the task, it then selects what is called a Z vector. This is a set of instructions that basically tells the brain which parts to emphasize to best handle the task. In other words, this Z vector tells the model how to adjust its dials and knobs and how much to adjust them in order to do better at a certain task. Anyways, the second method is called classifier-based adaptation. This basically uses a separate pre-trained AI called the classifier. So it's pretty simple. It just takes your input prompt and runs it through this classifier AI, which would identify what type of task this is. And again, based on the task, it will select a corresponding z-vector, which would tell this AI model how to adjust itself to best handle the task. And then the final method is called few-shot adaptation. This is used when you don't have a specific prompt or classifier to rely on. So in this case, it combines multiple pre-trained z-vectors. Again, these are the instructions on how to reconfigure the brain, and it uses a simple optimization algorithm to figure out what's the best combination of z-vectors to use. So those are the three methods to identify your incoming prompt, and then after it has identified your task, like is it math, is it coding, then it basically sends the z-vectors to modify the model. And this allows the model to emphasize the component of the brain that works best at solving the task, while also suppressing other components that are less relevant. And this simple tweak can make the AI way better at solving your question. Note that this is an AI architecture that can adjust its model weights during test time, or when you're actually using it, not just during training. So similar to the TITANS model, this seems to be a new trend. We're now seeing newer designs of AI models being able to change their configurations even after training. And with this two-step process, this allows the Transformers² model to adapt in real time and optimize its performance based on the task. Anyways, that sums up the architecture of this Transformers² and how it works. Next, let's look at how this actually performs compared to other models. So in this figure, it's comparing the performance of Transformers² with another model, Llama 3.8b, and it's comparing its performance across different subjects like math, coding, reasoning, and vision language. Now, this graph is actually not intuitive to understand, so let's go through it thoroughly. This black dashed line is actually the performance of Llama 3, and then this blue line is the performance of the Transformers² model during training, and the red line is its performance on a separate test set. So you can say the red line is really the most important line here. This indicates how well the Transformers² model does in the wild. And as long as this red line is above the dashed line, then it signifies that this is better than Llama 3. Now, as you can see for math, reasoning, and vision language, the red line is above the dashed line. So for the most part, it does beat Llama 3. However, note that for coding, interestingly, it actually does worse than Llama 3 with more training. Anyways, here's another table showing the performance of this Transformers² architecture across math, human eval, and arc challenge benchmarks. Now note that you can actually add this Transformers² architecture to any model like Llama 3.8b or Mistral 7b or Llama 370b. So this is a very flexible tool. It's model agnostic. And I'm curious what would happen if we added this to an even better model like DeepSeek or Qwen. Anyways, note that for the most part, adding this Transformers² architecture on top of a model increases its performance across most of these benchmark scores. Note that the bold value is the highest score out of all these options. Plus note that a green value means it's an improvement compared to the base model. So note that for the most part, these values from adding this Transformers² architecture are indeed green. So here's their conclusion from all of this. Transformers² represents a significant milestone in the evolution of AI systems. Its ability to dynamically adapt to unseen tasks in real time demonstrates the potential of self-adaptive LLMs to revolutionize AI research and applications. But this is just the beginning. Transformer² offers a glimpse into the future where AI systems are no longer static entities trained for fixed tasks. Instead, they will embody living intelligence, models that continually learn, evolve, and adapt over time. Imagine an AI capable of seamlessly integrating new knowledge or adapting its behavior in real-world environments without retraining, much like how humans adjust to new challenges. I mean, it's only January of this year, but we've already seen these two major breakthroughs of new AI architectures being able to learn and change its own configuration in real time. And I think we're going to see more of this. This unlocks a new wave of intelligence where AI models can keep learning and improving over time as you feed it more data. I think this is the end of what they call static AI models, or basically the old transformer architectures which can't really get better over time. Anyways, that sums up my review of these two papers. Hopefully this was easy to understand. I know both of these papers are quite technical, so I actually had to spend a few days reading and rereading these papers to really digest everything in order to explain it to you. Let me know what you think of all of this. Do you think this will be the end of the Transformer era? And do you think we're going to start seeing new AI models that can continuously learn and are way better than the best models we have right now? Let me know in the comments below. As always, I will be on the lookout for the top AI news and tools to share with you. So if you enjoyed this video, remember to like, share, subscribe, and stay tuned for more content. Also, there's just so much happening in the world of AI every week. I can't possibly cover everything on my YouTube channel. So to really stay up to date with all that's going on in AI, be sure to subscribe to my free weekly newsletter. The link to that will be in the description below. Thanks for watching, and I'll see you in the next one.